You know, there's a really common assumption we all tend to make. Making a system more efficient always makes it better. We see it everywhere, right? In businesses, in the technologies we use, even in our own daily habits. But there's a rather disturbing reality here. Relentless improvement actually guarantees systemic paralysis. We're going to explore an explainer of how a hidden architecture ensures that trying to be perfect is exactly how things break.
When we strip a system of its inefficiencies, it inevitably loses its ability to adapt to a changing environment. It seems counterintuitive, but optimization essentially eliminates alternatives. We believe we're building a better machine, but, as you'll see, we're actually building a trap.
Section 1. The Paradox of Improvement. Let's look at a really simple, observable physical system to understand this. Picture a heavy cart carrying goods across a wide-open, completely flat dirt field. Right now, it can go anywhere. It possesses infinite potential paths and total adaptability. But then a totally rational local optimization occurs. A specific route is chosen. By making the logical choice to take the absolute shortest route across the field every single day, the heavy cart's wheels slightly carve into the dirt. The ruts deepen, the wheels conform.
Efficiency seeks the shortest path. It's a continuous incremental effort to reduce suboptimal movements and save energy. I mean, this is the very definition of continuous improvement in action.
Section 2. The Cost of Efficiency.
With every single trip along that exact same path, those once shallow dirt tracks become deeper, and suddenly a subtle structural constraint emerges straight from the ground itself. The system is actually changing its environment. Staying in the rut requires less energy. Think about it. Steering that heavy cart out of the groove and onto fresh dirt now carries a physical and mechanical cost. The familiar inefficiency of the rut becomes far easier to maintain than trying to explore unknown optimizations outside of it.
A very strange behavior emerges here. Potential losses begin to weigh far heavier than equivalent gains. The system actually evaluates change asymmetrically. The physical effort required to push those heavy wheels up and over the dirt wall vastly outweighs the theoretical benefit of finding a new, better path.
This structural behavior actually has a name. It's known as status quo bias. It's a non-rational preference for maintaining the current state of affairs. Systems avoid necessary change due to the sheer cognitive cost of choice and a really deep aversion to loss. Notice that this isn't human error. It is an engineered reality.
Before we continue, I just want to briefly mention Sift. It's a news app I built that provides a calmer way to stay informed. It highlights only the most important news without endless headlines or sensational content, and you can find the link in the description. All right, let's return to our field.
Section 3. The Weight of Previous Choices.
Returning to the field, that continuous local optimization has rapidly escalated. The shallow dirt ruts have worn into deep, inescapable trenches. The system is fundamentally locked into the environment it created. And so, the system modifies itself perfectly to fit this new constraint. To survive the harsh, narrow trench, the cart's wheels must be heavily reinforced. The durable capital equipment is permanently altered to fit a highly restrictive, unforgiving environment.
What we see now is that past decisions strictly constrain all present movements. The choices made in the past have created dynamic, increasing returns. Every single trip deepens the trench, justifies the reinforced wheels, and makes alternative routes mathematically impossible.
This phenomenon is called path dependence. It's where past events or decisions strictly constrain later events or decisions. A primary event sets off a nearly uninterruptible chain of deterministic constraints. The cart literally can no longer leave the trench. It's simply no longer built for the open field.
We actually observe this architecture in reality all the time, where a 19th century decision completely locks in the 21st century. Take the standardization of railway track gauges in the 1800s. That was an early optimization that rigidly locked in the spatial dimensions of our global infrastructure today. The width of a highly advanced modern train was decided centuries ago by the width of a dirt rut.
Section 4. The Illusion of Alternatives.
At this point, the system reaches its final stage of optimization. That deep dirt trench is finally paved with steel to completely eliminate all friction. The adaptable wooden cart has been officially transformed into a railway train. Systems produce their own pattern of behavior. We're no longer observing isolated parts, just a wheel, a dirt path, or a steering mechanism. We're looking at a highly interconnected whole where continuous incremental steps have fundamentally altered the entity's very nature.
This is the absolute essence of systems thinking. It's examining complexity in terms of wholes and relationships. Interconnectedness means every single local improvement aggressively tightens the global knot. Optimize the track and you must optimize the wheel. Optimize the wheel and you completely lose the steering.
We find that perfectly rational local optimization creates inevitable global fragility. Each rational incremental decision to reinforce the wheels or pave the trench was entirely logical in the moment. Yet, those exact same decisions directly engineered an inescapably fragile outcome.
Section 5. Irreversible structural lock-in.
The train is now flawlessly efficient. It moves thousands of tons of goods with virtually zero friction. But if its required destination moves even 1 single degree off those tracks, the entire apparatus is completely paralyzed. The loss of alternatives is a mathematical certainty. This total inability to adapt is not an accident. It's not a failure of leadership, and it's not human error or a lack of imagination. It is the ultimate, inescapable consequence of hyperoptimization.
We are forced to realize that continuous improvement creates absolute rigidity. The complete lack of alternatives was engineered by the exact same mechanism that was designed to make the system better in the first place.
When we watch these complex systems inevitably collapse under the weight of their own perfection, we are left with one stark realization. The system was never failing. It was following its structure.